Next time you're sitting in a window seat on a commercial flight, just looking out at the clouds, I really want you to think about what's actually happening.
It's pretty wild when you actually stop to consider it.
Right. You're sitting inside, roughly 400,000 pounds of aluminum and steel. You're sipping a cup of coffee, casually suspended 7 miles above the earth, floating on what looks like absolutely nothing.
I mean, it honestly defies common sense.
It really does. Like, how is that heavy machine not just falling out of the sky? Welcome to another deep dive. Today, our mission is to answer that exact question.
That's going to be a fun one.
Yeah, we're taking some highly rigorous aviation physics, the core principles of flight, and we're stripping away all the intimidating math. We're going to decode the invisible physics that make the everyday miracle of human flight possible.
It's one of the most phenomenal subjects to break down because, when you look at an airliner on the tarmac, it just looks impossible. But once you start to visualize the actual mechanical forces at play, it stops being magic.
It becomes just physics.
Exactly. It reveals itself as this beautifully delicate, constantly shifting balance.
Okay, let's unpack this, starting with the biggest illusion of all, the idea that a plane is flying through nothing. Before we can understand how a plane flies, we have to talk about what it's flying through.
The atmosphere, which is the perfect starting point, really, because the atmosphere isn't just empty space. In the realm of physics, air acts as a fluid.
Like water.
Very much like water, yeah.
Okay.
It has mass, it exerts physical pressure, and it has viscosity, meaning it resists flow.
So we're essentially swimming, and this fluid is mostly nitrogen, right? Like 78% nitrogen, 21% oxygen, and some trace gases.
That's the chemical makeup, yeah. But the real challenge for aviation is the atmosphere's unpredictability. I mean, it's hot one day, freezing the next, humid in the morning, dry in the afternoon.
Which is a nightmare for math.
Right. If you're an aerospace engineer designing a wing or a pilot calculating runway length, you cannot rely on random daily weather. You need a constant. So the aviation world uses the International Standard Atmosphere, or ISA.
It's basically a mathematically perfect baseline weather day.
Exactly. A hypothetical environment for all performance calculations. In the ISA model at sea level, the standard pressure is 1,013.25 hectopascals.
Okay.
The baseline temperature is 15 degrees Celsius, and the air density is 1.225 kilograms per cubic meter. It also assumes the air is bone dry, zero humidity.
Let's contextualize that density number for a second, because 1.225 kilograms per cubic meter sounds a bit abstract.
Sure.
A cubic meter is roughly the size of a standard household washing machine. That means if you capture a washing machine-sized block of invisible air at sea level, it actually weighs over a kilogram.
Yeah, it has real physical heft to it.
Which is crazy to think about.
And that heft changes at a very predictable mathematical rate as you climb. It's called the standard lapse rate. In our perfect ISA model, the temperature drops by about 1.98 degrees Celsius for every 1,000 feet you go up.
Wow, that's fast.
It is. And this cooling continues steadily until you hit about 36,090 feet, the upper limit of the troposphere. At that specific altitude, the temperature stops dropping and permanently freezes at negative 56.5 degrees Celsius.
Which explains why your window is always freezing cold at cruise altitude.
Yeah.
But beyond temperature, the real metric an airplane cares about is density, right?
Density is king. The thicker the fluid, the better the wings and engines work. High density gives you incredible performance. Low density severely degrades it.
So what controls the density?
3 things, basically: pressure, temperature, and humidity. High atmospheric pressure literally squeezes the air molecules closer together, and cold temperatures cause those molecules to slow down and pack tighter.
So a cold, high-pressure day means incredibly dense air.
Exactly. The plane will just leap off the runway.
But humidity is the variable that always trips me up. When I walk outside on a sweltering, highly humid summer day, the air feels incredibly thick and heavy to me.
Right, it feels oppressive.
But aerodynamically, high humidity actually lowers air density. It makes the air thinner. That just feels wrong.
It's a fantastic paradox. You have to look at it on a molecular level. Water vapor molecules, H2O, are physically lighter and smaller than dry air molecules like diatomic nitrogen and oxygen.
Oh, I see.
Yeah, so when you pump a massive amount of water vapor into a specific volume of air, those light water molecules crowd out and displace the heavier ones. The total volume stays the same, but the overall mass drops.
So a hot, incredibly humid day with low barometric pressure is essentially an airplane's worst nightmare.
Pretty much. The air is thin, the engines gasp for breath, and the wings have less mass to push against.
Okay, so we're navigating this invisible ocean of fluid, and it gets thinner as we climb. When a plane is flying straight and level at a constant speed, it reaches a state of perfect equilibrium.
Yes, Newton's laws take over. The four forces of flight hit a stalemate.
The lift pulling the plane up perfectly matches the weight pulling it down. And the thrust from the engines pushing forward perfectly matches the aerodynamic drag pulling backward.
It's a four-way tug-of-war where nobody is winning.
Which begs the biggest question of all. If we are swimming in this invisible, relatively thin fluid, how does the plane actually generate the immense upward force to fight hundreds of thousands of pounds of gravity?
To understand that, you really have to look at how a wing manipulates pressure. It all starts with a fundamental rule of fluid dynamics called the equation of continuity.
Which dictates that the flow rate of a fluid is an absolute constant.
Exactly. If you have water flowing through a wide pipe, and that pipe suddenly narrows down to half its size, the water doesn't just bunch up or compress.
It has to speed up. It races through the narrow section, so the same volume of water exits in the exact same amount of time.
Now, take that exact concept and apply it to the shape of an airplane wing. When undisturbed air meets the front of the wing, the leading edge, it has to split. Some goes under, some goes over.
Right, and on a standard commercial airplane, the top surface of the wing is curved, which is called camber, right? But the bottom is relatively flat.
You've got it. That curve on top acts just like the narrowing of the pipe. It creates a physical restriction, forcing the air traveling over the top into a narrower, tighter space.
So relying on that equation of continuity, the air traveling over the curved top of the wing has absolutely no choice but to speed up.
And this brings us to Daniel Bernoulli. Bernoulli's theory proves that in a steadily flowing fluid, the total energy of that system must remain constant.
Okay, so what makes up the total energy?
It's made of two things: kinetic energy, which is the speed of the fluid, and static pressure, which is the physical crushing weight of the fluid pushing in all directions.
It's a zero-sum game, basically.
Mm-hmm.
If one goes up, the other has to go down to keep the total energy perfectly balanced.
That right there is the secret to human flight. Because the curved wing forces the kinetic energy, the speed, to radically increase over the top, the static pressure on that top surface must radically drop to balance the equation.
So by merely speeding up the air, the wing produces a powerful pocket of low pressure right on top of itself.
It literally creates a vacuum on top of the wing, and the normal, higher pressure air flowing under the flat bottom just seeks equilibrium. It pushes upward, trying to fill that vacuum, and takes the airplane with it. That upward push is lift.
Wow, and all of that upward force concentrates at a specific focal point called the center of pressure.
Yeah, it generally sits right at the thickest part of the wing's curve, because that's where the restriction is tightest, the air is moving the fastest, and the vacuum is deepest.
And a pilot can manipulate this, right?
Mm.
As they pull back and raise the nose, they increase the angle at which the wing meets the wind, the angle of attack.
Yes. And as they do that, the center of pressure actually moves forward, closer to the leading edge, up to a very specific limit anyway.
Okay, here's where it gets really interesting, though. We just established that standard planes use asymmetrical wings, curved on top, flat on bottom, to act as that restriction. But what about fighter jets? I was watching a video of an F-16, and its wings are perfectly symmetrical. The top and bottom are completely identical, like a flat wedge. Wait, if a jet's wing is completely flat on both sides, how does it speed up the air on top to create that Bernoulli vacuum?
That is an excellent observation. If a perfectly symmetrical wing is flying dead level, perfectly parallel to the wind, the air splits evenly. The speed on top matches the speed on the bottom.
So there's zero pressure difference.
Exactly. Zero pressure difference, and therefore absolutely zero lift. The plane would fall like a rock. But symmetrical wings bypass the built-in curve by relying entirely on their angle of attack.
They tilt the whole plane. It's like when you're a kid riding in a car and you stick your flat hand out the window.
Yes, the classic example.
If your hand is level, the wind just glides over it. But the second you tilt the front edge of your hand up, the wind violently throws your arm toward the roof.
That is exactly the Venturi effect in action. By pitching the nose of the plane up relative to the wind, the pilot physically forces the flat bottom of the wing to act as a deflector, compressing the air below.
And meanwhile, the top of the wing is angled away from the airflow.
Right, so the air has to aggressively wrap around that tilted leading edge and rush over the top to fill the void. The angle itself creates the restriction, speeding up the air and dropping the pressure, even without a physical curve built into the metal.
So asymmetrical wings, like on a Boeing 737, generate lift naturally and efficiently at a flat cruise angle. But symmetrical wings on a fighter jet force the pilot to fly slightly pitched up to get the same effect.
Which allows them to easily fly completely upside down without losing altitude.
Right. So we've manipulated the air, we've got our lift, we're officially defying gravity. But as you always hear, the universe demands a tax. In aviation, the price you pay for manipulating a fluid is drag.
And drag completely complicates how a pilot understands their speed. Speed in an airplane is nothing like a speedometer in your car, which just measures how fast the tires are spinning.
Right. An airplane measures speed by ramming air into a forward-facing probe called a Pitot tube.
Yeah, but what the dial reads in the cockpit is rarely the reality of how fast the plane is moving through the air mass.
And the aviation mnemonic for remembering all the different types of airspeed is iced tea is a pretty cool drink.
It sounds absurd, I know, but it maps out the speeds and the physical errors beautifully. ICE-T stands for ISCAEASTS. That is indicated, calibrated, equivalent, and true airspeed.
And pretty cool drink represents the errors you have to mathematically subtract position, compressibility, and density errors.
Exactly. So IS indicated airspeed is just the raw, uncorrected number the pilot sees on the dial.
But because the pitot tube is mounted on the outside, and the plane might be flying at a weird angle, the wind might not be hitting the tube perfectly straight on. That creates position error.
Right. And if the computer corrects for that angle, you get CAS, calibrated airspeed. But if you're flying in a jet above 200 knots, the sheer force of hitting the air causes the molecules to physically compress as they jam into the tube.
Artificially inflating the pressure reading.
Exactly. That's compressibility error. Once you correct for that, you get EAS, equivalent airspeed.
And finally, the biggest factor of all, density error. Because, like we established earlier, as you climb, the air gets incredibly thin.
There are just fewer air molecules physically available to ram into the sensor. You have to correct for how thin the air is to find your TAS, your true airspeed.
Which is the actual physical speed the aircraft is moving through the block of air around it.
Yeah. As a general rule of thumb, true airspeed increases by roughly 2% over indicated airspeed for every 1,000 feet you climb.
Oh, wow.
So up at 30,000 feet, the dial in the cockpit might say 250 knots. But because the air is so thin, the plane is actually tearing through the air at well over 400 knots.
So knowing how fast we're truly moving, we need to look at what's actively trying to slow us down. The drag, the forces fighting our thrust. This gets split into two wildly different categories, right?
Yes. The first is parasite drag, which is exactly what it sounds like. It's a parasite on your forward momentum.
It's just the physical resistance of moving an object through a fluid.
Exactly. It's a combination of three things. First is form drag, which is simply the geometric shape of the plane. A sleek fighter jet has less form drag than a bulky cargo plane.
Makes sense.
Second is skin friction. This is fascinating at a microscopic level. There's a boundary layer of air right against the surface of the wing where the air molecules literally get trapped in the microscopic pores of the metal.
They just stick to the wing.
Yeah, they slow down to zero velocity, acting like liquid sandpaper. And third is interference drag, which is the turbulent, chaotic wake created wherever two separate parts of the plane join together at sharp angles.
Like where the wing roots into the fuselage. Which explains why modern planes are so incredibly smooth, using those sweeping fiberglass fairings to cover up all the joints. They're desperate to reduce interference drag.
Absolutely. But the second category of drag is the truly mind-bending one, induced drag.
Right. Induced drag is the inescapable byproduct of creating lift, because you have a high-pressure air trapped under the wing and a low-pressure vacuum on top. And nature absolutely disguises an imbalance.
Wants to equalize that pressure immediately.
So at the extreme left and right tips of the wings, that high-pressure air from underneath suddenly finds an escape route. It violently curls up and over the wingtip, trying to flood into the low-pressure vacuum on top.
Creating massive horizontal tornadoes trailing behind the wingtips, known as wingtip vortices. And those vortices are extraordinarily powerful. They can trail behind a heavy airliner for miles.
They could even flip smaller aircraft upside down, right?
Easily. But for the airliner creating them, those tornadoes induce a powerful downward flow of air right behind the wing called downwash. That downwash effectively tilts the airplane's total lift vector slightly backward.
So instead of all your lift pointing straight up to fight gravity, a chunk of it is pointing backward, actively pulling the plane backward.
Exactly.
Now, if I'm driving my car and I want to reduce wind resistance to save gas, my immediate instinct is to just slow down. But if I'm understanding this correctly, airplanes operate under a completely inverted logic.
What's fascinating here is that slowing down an airplane triggers a catastrophic chain reaction of drag.
Yeah.
If you reduce thrust and slow down, you start losing your kinetic speed over the wing, which means you lose your lift.
Then to avoid falling, you have to pull back on the yoke, increasing your angle of attack to scoop more air.
Right. But a high angle of attack creates a massive pressure differential between the top and bottom of the wing.
Which creates absolutely gigantic wingtip vortices.
Precisely. By slowing down, you exponentially increase your induced drag. Parasite drag goes up when you fly fast, because you're physically ramming into the yaw. But induced drag goes up when you fly slow because your angle of attack is so steep.
So to get maximum aerodynamic efficiency, you have to find the exact speed where those two drag curves intersect.
Yes. This is known as VMD, or minimum drag speed. It's the holy grail of efficiency.
It yields the best lift-to-drag ratio, the maximum fuel range, and terrifyingly, if you lose all your engines, pitching to fly at exactly VMD ensures you'll glide the furthest possible distance.
It's the most critical speed to know.
Okay, so we've got lift pulling up, drag pulling back, gravity down, thrust forward. With all these massive forces constantly shifting, how does a pilot actually manipulate this delicate balance without physically exhausting themselves?
Well, it requires controlling the aircraft along three distinct invisible axes. First is the lateral axis, which runs wingtip to wingtip. A pilot controls pitch nose up and down using the elevator on the tail.
Second is the longitudinal axis, running nose to tail.
Right, you control roll banking the wings using the ailerons on the trailing edges of the wings. Finally, the vertical axis runs straight down through the center of the plane. You control yaw, the side-to-side sweeping of the nose, using the rudder pedals.
But the reality is that moving one of these controls never happens in a vacuum, right? You trigger secondary effects.
Always.
Like if I step on the rudder pedal, the nose yaws to the left. But as the nose sweeps left, the entire right wing sweeps rapidly forward through the air. And because it's moving faster, it generates more lift.
So the secondary effect of yawing is that the plane also rolls.
Wow.
And the secondary effects of the ailerons are even more complex and heavily tied to that induced drag we just discussed. If a pilot turns the yoke to the right, the left aileron droops down, creating more lift to raise the left wing.
And the right aileron pivots up, decreasing lift and dropping the right wing.
Exactly. But because that left wing is suddenly producing significantly more lift, it is fundamentally producing much more induced drag.
Oh, and that drag acts like a giant parachute tied to the left wingtip, anchoring it backward. So I turn the yoke to bank right, but the nose of the plane violently yaws to the left.
Yes, that is called adverse yaw. It's like turning the steering wheel of your car to the right, but the hood swings into oncoming traffic before it finally turns.
That sounds incredibly disorienting for passengers.
It is. So aeronautical engineers designed brilliant mechanical workarounds like the freeze aileron. It's designed on an offset hinge. When the right aileron pivots upward, the front lip of it actually dips down into the high-speed airflow underneath the wing.
Intentionally creating parasite drag on the right side.
Exactly. It acts as a brake on the right side, completely canceling out the adverse yaw from the left side.
That is just brilliant engineering, using drag as a tool rather than an enemy. But this constant tinkering highlights the ultimate tug-of-war in aviation design: stability versus controllability.
You truly cannot have both. Stability is an aircraft's natural aerodynamic desire to return to straight and level flight after being disturbed by a gust of wind.
And controllability is how quickly the pilot can force the plane to change direction.
Right. Passenger airliners are engineered with positive dynamic stability. If you let go of the controls, they desperately want to fly straight. This makes them incredibly safe, but they feel heavy and sluggish to maneuver.
Whereas a fighter jet is designed to be inherently unstable.
Completely unstable. It wants to flip out of control at a moment's notice, which gives it terrifyingly fast maneuverability. But it requires advanced computers making thousands of micro adjustments a second just to keep it flying in a straight line.
And a major factor dictating that stability is the center of gravity, or the CG, where the physical weight of the fuel and passengers is balanced.
Yes. A forward CG, meaning the plane is nose-heavy, creates a long leverage arm back to the elevator on the tail. It makes the plane incredibly stable, but it makes the yoke feel really heavy for the pilot to pull.
And conversely, an aft, or rearward CG, means the plane is tail-heavy. This actually makes the plane cruise faster and stall at a slower speed, but it's deeply dangerous, right?
Extremely dangerous. It destroys longitudinal stability. The plane becomes twitchy, eager to pitch its nose up uncontrollably.
Which brings up the physical reality for the pilot in the seat. How heavy do these controls actually feel? If I'm flying really fast versus coming in for a slow landing, is the physical resistance the same?
It changes drastically based on the airflow. At cruise speeds, millions of dense air molecules are battering the controls every fraction of a second. The controls become incredibly stiff.
So just a tiny twitch of the wrist causes a dramatic movement.
Right. But at low speeds, like an approach to landing, the airflow is weak. The controls feel mushy and sloppy. The pilot has to make massive, sweeping rotations of the yoke just to get a sluggish response.
But if the controls get stiff and heavy at high speeds, and the plane's center of gravity makes it nose heavy, how does a pilot hold the yoke back for a 5-hour flight without their arms cramping up?
They use trim tabs. These are tiny, hinged mini flaps attached to the trailing edge of the main flight controls. And the genius is that they use the air to do the manual labor.
So if a pilot needs the main elevator on the tail to stay tilted UP, they use a dial in the cockpit to pitch the tiny trim tab down into the wind.
Yes, the high-speed airflow hits that deflected tab, and the physical force of the wind leverages the massive main elevator upward for them. It completely neutralizes the aerodynamic pressure, reducing the physical stick force to zero.
That's amazing. There's also a mention of mass balancing in these notes, which sounds like putting weights on a car tire, but in aviation, it's used to prevent control flutter.
Control flutter is a catastrophic phenomenon. At high speeds, if the center of gravity of an aileron is sitting behind its hinge point, the aerodynamic forces can cause it to start vibrating rapidly.
Like violently vibrating.
So violently that it can physically rip the control surface off the wing in seconds. To fix this, engineers bury heavy lead weights in the leading edge of the control surface, forward of the hinge, to perfectly balance the mass and neutralize the vibration.
Wow. Okay, we've covered straight and level flight. We've balanced the center of gravity, trimmed the controls, we're cruising efficiently. But the true test comes when we push the aircraft out of equilibrium. Let's look at turns, load factors, and the stall.
When a pilot enters a bank to turn, they're taking that vertical lift vector that was fighting gravity and tilting it sideways.
A significant portion of your total lift is now being hijacked to pull the plane horizontally.
Exactly. Which means you suddenly don't have enough vertical lift remaining, and the plane will begin to descend.
So to maintain altitude in a steep turn, the pilot has to pull back on the yoke, increasing the angle of attack to force the wings to generate more total lift to compensate.
And that introduces load factor. It's exactly like hitting the bottom of a steep loop on a roller coaster. You momentarily feel twice your normal body weight.
Because in an airplane, the math dictates that if you enter a steep 60-degree banked turn, the load factor exactly doubles to 2.0 G.
Right. So if the aircraft weighs 2,000 pounds, rolling into a 60-degree bank means the wings are instantly forced to support 4,000 pounds of aerodynamic force.
And because you're asking the wings to do double the work, you're pushing them much closer to their absolute aerodynamic limit, which leads directly to the stall. Now, just to be clear, in a car, stalling means the engine died. In an airplane, an aerodynamic stall has absolutely nothing to do with the engines.
Nothing at all. An aerodynamic stall occurs when the wing exceeds its critical angle of attack. If you tilt the nose of the plane too far up into the incoming wind, the air flowing over the top of the wing can no longer physically bend around that steep curve.
The smooth airflow violently detaches from the metal.
Exactly. It becomes a turbulent, bubbling wake. The Bernoulli vacuum is instantly destroyed, your lift plummets, the nose drops, and gravity wins.
But the crucial takeaway here is that the critical angle of attack never ever changes. It is a fixed geometric limitation of how that specific wing is shaped.
The angle is fixed, yes, but the speed at which you hit that angle changes constantly. If you load an airplane with heavy cargo, or if you enter that 60-degree turn and double the G-load, the wings have to work significantly harder just to maintain level flight. That means the pilot has to fly at a much higher angle of attack just to cruise.
Because they're already flying so close to that critical angle, any slight disruption will cause a stall. So a heavy plane, or a turning plane, will stall at a much faster airspeed than a light plane.
Which is exactly why airliners deploy those massive flaps when they come in to land. By extending flaps, they change the shape of the wing, increasing the camber and surface area, allowing the wing to generate massive lift at very slow speeds without hitting that critical angle.
But what happens if a pilot messes up and enters a stall? The physics outline two terrifying descent scenarios: the spiral dive and the spin.
To a passenger, they might look identical, but aerodynamically they are opposites. A spiral dive is a steep turning bank where the nose drops and the plane just accelerates toward the ground. Crucially, The wings are not stalled. The airspeed indicator will be rapidly increasing.
And a spin.
A spin is a complex, fully stalled condition. What happens is the plane stalls, but it's uncoordinated. One wing stalls slightly deeper than the other and drops. This throws the aircraft into auto-rotation.
So it's spiraling downward like a falling leaf.
Yeah, and the wing pointing down meets the oncoming air at a much steeper angle, keeping it deeply stalled with massive drag. The wing pointing up is slightly less stalled, so it produces a tiny bit of lift. This imbalance locks the plane into a twisting corkscrew. And unlike a spiral dive, the airspeed in a spin is remarkably low and constant.
So if a pilot finds themselves falling out of the sky in a twisting spin, the natural screening human instinct is to pull back on the yoke to try and make the plane go up. Why is that the exact wrong thing to do?
Well, if we connect this to the bigger picture, you have to remember the golden rule: a spin is just a stall. If you panic and pull back on the yoke, you are taking wings that have already exceeded their critical angle of attack, and you're forcing them even higher.
You're deepening the stall.
Exactly. You increase the drag and tighten the rotation of the spin.
You're actively making the problem worse while trying to save yourself. So to break a spin, the pilot has to forcefully push the control column forward, driving the nose further down toward the ground to force the angle of attack below that critical limit.
You have to unstall the wings. And at the same time, you stomp on the rudder pedal opposite to the direction of the spin to forcefully stop the rotation. Only after the wings reattach to the smooth airflow can you gently pull back to recover.
It is the ultimate test of trusting the physics over your own visceral panic. Well, we've covered a massive amount of ground today. We started by defining the invisible, mathematically perfect ISA fluid of the atmosphere.
We really went through it all.
We explored how wings manipulate that fluid to create Bernoulli pressure vacuums. We unpacked the endless tax of induced drag, adverse yaw, trim tabs, and finally pushed the absolute limits of load factors and stalls.
It's a phenomenal reminder that the air around us isn't empty space. It is a tangible, powerful force if you understand the mathematics governing it.
And that leads me to a final thought for you to take away today. While we've been talking strictly about airplanes, these exact same aerodynamic laws govern our everyday world down here on the ground. Think about induced drag and those violent wingtip vortices that pull an airplane backward.
Oh, like on wind turbines.
Exactly.
Yeah.
That physical phenomenon is the exact reason why modern wind turbines have strangely curved, swept-back blade tips. Engineers realize straight blades create massive vortices that drag the blades backward, reducing power generation. The curved tips physically block the high pressure from escaping, killing the vortex and increasing efficiency.
That's incredible.
Or think about Formula One race cars. An F1 car is essentially an upside-down fighter jet. They use inverted, perfectly symmetrical aerofoil spoilers and pitch them at aggressive angles to intentionally create the Bernoulli vacuum effect on the bottom of the wing,
generating negative lift.
generating thousands of pounds of negative lift to physically pin the car to the asphalt at 200 miles an hour. The physics of the sky are actively shaping the technology on the ground everywhere you look. It's something to keep an eye out for on your drive to work. Thanks for diving deep with us.